workshop. Wonderful. All right, so thank you everyone for making it. We have a really exciting workshop for everyone today. So we have over 250 students that are joining us both in person and remotely that are going to be watching this offline from over 9 countries doing this workshop. So we're really, really excited to go and welcome all of you and let you all learn from what we've put together. So at a very high level, before we go into the workshop, I want to kind of discuss what we'll actually be doing today. So the file that I sent to all of you a little earlier, it's medical data. And what we're doing is that we're asking the question, based on this medical data for post-surgical cancer patients, that's people with cancer who just got a surgery, can we use machine learning to predict who will live and who will die? So to kind of put yourself in the shoes of these patients, imagine, and I hope none of you are ever in this situation, imagine that you get diagnosed with something like lung cancer, and you go into the doctor, and the doctor gives you surgery, and they remove that lung cancer. So right after that surgery, at that exact point, can I say that you are at risk of dying within 30 days, or you are fine and you're not at risk of dying within 30 days? So that's kind of what our ultimate goal is. And this variable here, the variable of who lives and who dies within 30 days is called DOPR2D. That's really not important right now. I'll cover it later, but I'm just kind of giving it as a broad overview so you will have it in the back of your minds. So to kind of go into a conceptual overview before we can study what is machine learning, I guess the prior question that we have to ask is, what is learning? How do we as humans learn? So for the first kind of 10 minutes of this workshop, I'm going to go and take us all the way back to primary school, all the way back to preschool, first grade, and we're going to go and think about how did we learn about dogs and cats when we were little? And it seems very, unrelated, but I promise you it's very, very important and very, very related to our core subject at hand. So back all the way when we learned what was a dog and what was a cat, before we even knew what a dog and cat was, we had our teachers. And our teachers went and showed us lots of images of dogs. And they said, oh, look at this thing that has pointy ears, that says woof, that barks, that eats dog food. This is a dog. And they gave us multiple images of dogs and multiple images of cats. And we were able to learn from them. And we were able to identify patterns and analyze and say, what is a dog? What looks like a cat? And then we were able to go and identify dogs and cats out in the wild, out in the park, even if we've never seen that exact dog or cat before. So to kind of break this down, this is a core outline for today. So this is how we break down how, I guess, knowledge happens, how we learn. And it's actually exactly how machine learning works as well. So the steps are train, test, and assess. So to kind of break this down, the first step is you train on data, which means that I show you a lot of images of dogs and cats, and I show you, you read those little childhood books, and they have lots of pictures of dogs, pictures of cats, and they tell you that this is a dog, this is a cat, and they tell you what's going on. They label it. So that's kind of the studying phase. The training phase is more studying, learning associations, understanding, well, what is really going on. The second step is testing. Testing is applying what you've learned on new material. So if training is looking at lots of dogs and cats that I've learned, testing is looking at a new image of a dog I've never seen before, and me applying the knowledge I have and saying, oh, this is a dog, this is a cat. So this is very much like when you went and took an exam in school. And assessing, the last step, is basically like you get your grade for the exam. You see out of all the dogs you see, how many were you able to correctly identify and say, this is a dog? How many were you wrong on? So maybe you got 90%, maybe you got a B, maybe you got an 80%, so on and so forth. So to kind of go and hit this point home, the training step is when I see multiple images of dogs and they're all labeled dogs. So I'm telling you that this is a dog, I'm telling you that this is a dog, and I'm telling you this is a cat, this is a cat. And you are forming associations and saying, well, it looks like this has pointy ears, looks like they have a tongue like this, looks like they eat mice and they have whiskers like that. And you're forming these associations. And then lastly, the testing phase is when, even though I've never shown you this cat before, based on all these cats that you've seen, you can say that, oh, generally cats have pointier ears, a sharper nose, a shorter snout. So this is probably a cat. And even if you've never seen this before, you've never seen this dog before, you've only seen these dogs, you can still apply what you've learned and say, oh, they have flappy ears, they bark, so on and so forth, and that this is a dog. So now the next step is kind of getting an accuracy score. An accuracy score is maybe out of 10 cats I saw, I was able to correctly identify 9. So I have a 90% accuracy, 80% for dogs, whatever. So that's kind of how we assess our accuracy in school when we get testing and grades. And it's actually very similar in machine learning. And the last concept that I want to teach about is an AUC ROC curve. This is probably the most complicated or new concept that we'll have to go through for all of the workshop. But essentially, what an AUC ROC is that AUC stands for area under the curve. ROC, and that's not important, is called receiver operating characteristic curve. But that's basically just this curve. It's called an AUC ROC. So essentially all it does is it puts your true positives against your false positives. So this is true positive rate, false positive rate. So a true positive is if I say something is a dog and it's actually a dog. In the cases of cancer, a true positive is when the doctor says you actually tested positive for cancer and you actually do truly have cancer. A false positive is if I said this is a dog, but it's actually a cat or a tree or something. In medicine, a false positive is if I say you have cancer, but you actually don't have cancer, and it was a false positive. So an AUC ROC graph basically shows how well are you at identifying true positives? How well are you at identifying who is actually a dog or who actually has cancer? And then it gives you this ROC curve. So this line in the middle is a reference line. This line means that you have no discrimination ability. This line in the middle means that you can identify as many true positives as false positives. So you're guessing at random. So this line, if your actual AUC ROC is this line, that's very bad. But you want your AUC ROC to be something like this. So that means you have lots of true positives. You can correctly identify, like dogs, or correctly identify cases of cancer without having false positives, without falsely identifying cases of cancer or falsely identifying a dog in our example. So that's what an AUC ROC curve is. It's very, very important in machine learning. And there's lots of, every time someone does a machine learning model, you have this kind of AUC ROC curve to show you how good are you at identifying some kind of positive case. So this kind of takes us back to our core outline one last time, and I'm really going to be hammering this in. So I'm going to repeat this multiple times, but this is exactly how machine learning works. The first step is that you train your model, and that's when we look at lots of images of cats and dogs, and it's pre-labeled, and our teachers tell us this is a cat, this is a dog. And we learn what is a cat and what is a dog. And we form these analysis of these patterns. And we learn that, dogs have floppy ears, cats have pointy ears, one says wolf, one says meow. And we form these patterns. Then we test and we apply what we've learned and ask, can we identify new cats and dogs that we've never, ever seen before in the park or something? And then the last step is assess and see what is your accuracy? Can you identify 50% of cats, 100% of cats, 90% of dogs? And you also have the AUC ROC curve to see how accurate are you in identifying true positives over false positives. So this is our core outline of training, testing, and assessing. Now, obviously, this is, you didn't come here to learn about identifying cats and dogs. Hopefully, you already know what cats and dogs look like and are. What we're here to learn about is, instead of cats and dogs and identifying what is a cat and what is a dog, can we identify what is cancer and what is non-cancerous in humans? And that's what this workshop really is about. But it's the exact same thing as identifying what is a cat and what is a dog. The same way that we as human beings learn what a cat and dog is, machine learning models, they learn just the way humans do, will identify what is cancer and non-cancer in a very similar way. So before I go into breaking down these steps, the one thing that I'm going to talk about is medical data frames. So a data frame, simply put, is it's a frame of data. It's a chunk of data that has columns of clinical features, they're medical features or just general features. So this is about age. These are all patients with age. This is smoker. Do you smoke? Yes or no? This is your gender. Are you male or female? And this all has rows. So every individual row is a new patient. So the data frame that we'll be working with is also very similar, where it has lots of columns of clinical features like age, gender, height, weight, all that kind of stuff. And every row is a new patient. So this patient is 71 years old, is a male, they have this kind of education, they did smoke, and they did have cancer. Whereas this patient over here is a 57-year-old male who didn't smoke and didn't have cancer. So every row here is a patient, and every column here is a clinical attribute or a different kind of attribute. So we can look at all the education levels or all of who smoked and didn't smoke, and every row gives you an individual patient. I'm kind of repeating this a lot, but it's hammering down the point of what a data frame is, and it's very, very important very shortly. So this kind of brings us to our whole case of what we're going to be studying today about disseminated cancer or metastatic cancer and who dies or who doesn't die with cancer. So this is a really, really big issue because even in our data that we'll be working with, 38%, so over 1 in 3 patients who goes in for surgery for cancer will die within 1 month. So that means that these are patients that go to get surgery, and within 30 days of their surgery, they die from some kind of complication. And that's really, really scary. And the scariest part here is that doctors are only right about 20% of the time. So they're only right in predicting who lives versus who dies for 1 in 5 patients, which means that for the remaining 4 out of 5 patients, doctors are wrong. They think you'll die when you actually won't die, or they think you'll live when you'll actually die. And that means that you get improper therapy, you don't get the proper kinds of treatments, and that leads to over 500,000 deaths each and every single year. So that's 600,000 deaths in the US alone. There's actually millions of deaths globally because of this issue. So the question we'll be asking is, can we use machine learning to achieve a better rate? Can we identify better than physicians who are only right 20% of the time, who will live versus who will die? And that's what the data we'll be looking at looks like. So just the same way that I said that as humans, this is how we as humans learn. And we say, this is a dog, this is a cat. We learn these features, we analyze, and then we identify new cases of dogs and cats we've never seen before. Our machine learning models are doing the exact same thing. So what our machine learning models are doing is that instead of taking in, instead of what we did where we looked at dogs and cats, now they're looking at patients with cancer and patients without cancer. So to keep it very simple, remember, every row is an individual patient. So this is patient number 1, this is patient number 2, this is patient number 1, patient number 2. So I give my machine learning model all these patients who I tell the machine learning model has cancer. So I say, look at this patient. He was a 71-year-old male. He did have cancer and he did smoke. So then the machine learning model is like, oh, the patient is a little older. They smoke. Maybe that's correlated with cancer. And you look at multiple images, multiple cases like this. In the second case, I say, oh, look at this, all these patients who don't have cancer. This patient didn't smoke, they're a little younger. This patient was a little younger, was female, didn't smoke. The machine learning model starts identifying these cases. So obviously I only have like 6 or 7 patients here. In reality, we're giving these machine learning models thousands of patients. When I train my machine learning models, I give them tens of thousands, hundreds of thousands of patients. So sometimes even millions of patients. The machine learning model really looks at hundreds of thousands, millions of cases of who does have cancer, who doesn't have cancer. And it's able to form these associations and form these extrapolations of, what constitutes who doesn't have cancer. Why do these people not have cancer? Maybe they're working in certain places. Maybe they aren't as educated or something. Maybe they're younger. Maybe these patients are older. All these kind of things. And the machine learning model is able to learn these kind of patterns that are incomprehensible to the human eye. That as a doctor, if I look at these thousands of patients, I can kind of see patterns, but machine learning models can see it to a lot more detail and be a lot more accurate here. And then after analyzing these cases, they're able to predict on new cases that the model has never ever seen before. So to kind of show you this up close, I give it these data frames of who has cancer, and I tell the model all these cases of they do have cancer. Look, all of these people have cancer, and the model knows they have cancer. And likewise, all these people don't have cancer. The model studies them. And then the model is able to apply for new data who I don't know if they have cancer or not. So I actually blind the model to what the correct answer is. Do they have cancer or not? And then the model makes predictions on everything the models learn, just the same way that we study for a test and we try to apply ourselves on the actual test. The model also tries to make its answers and say, I think this doesn't have cancer. This person does have cancer. And then you compare it against what they actually have. So what's very important to note here, and this is something that confused me too, is that these patients are actually part of our original data frame. So what we do in machine learning is essentially, we have a data frame of patients, and let's say we have 10 patients. Conventionally, we take about 80% of the patients. So we would take about 8 out of 10 patients, and we would train on them. So we would learn associations and say, okay, this patient does have cancer, this person doesn't have cancer. And on the last 20% of the data, the last 2 out of 10 patients, we would actually purposefully not look at the answer. So we actually do have the data for the last 2 people. So in this case, we actually do have the data of who has cancer, who doesn't have cancer, but we blind ourselves to it. Our model pretends to not see what the answer is, and the model makes an educated guess and predicts what the answer is, and only then does the model look at the actual answer and see if they line up. If this is complicated, I also got confused with this, but this is a really good analogy, I think. So when you're all studying for a test, let's say we're studying for a math test, you all know how we have practice problems in the book, and there's an answer at the end of the book. So it's a really bad way to study if you read a practice problem and you immediately look at the answer because you just saw the answer. You're not actually learning or doing any math, right? You're not making a prediction. So a good way to study is that, let's say the book problem is 1 + 1. and I have the answer in the back of the book. The best way to study is don't look at this. You do not look at the answer. You blind yourself to the answer. And then I say, oh, 1 + 1 in my head, I believe 1 + 1 is 2. And then when you make that prediction, only then you look at the actual answer and you say, okay, I thought it was 2. The actual answer is 2. I got 100%. Next problem. Or let's say I messed up and I was bad at math and I said, oh, 1 + 1, oh, that might be 10. And then if I look at the answer and it's actually 2, then I can say, oh, I guessed 10. The answer was 2. I got that wrong. I got a 0%. So that's exactly what our machine learning models are doing here, where they have they study on these cases and they know what the answer is. And then for a certain proportion of cases, the model blinds itself. So it knows that, we know what the answers to these are on the back of the book, so to speak, but the model blinds itself to this and makes an educated guess based on what it's learned. And then it compares it to what the actual answer was, kind of like this 1 + 1 example. And that's how we get our accuracy scores. So the model goes and says, okay, for the 10 patients, I predicted, 9 correctly. And the last one I thought had cancer, but they actually didn't. So I was wrong on that one. So that's how the model had a 90% accuracy here. And maybe the model had an 80% accuracy for predicting non-cancer healthy cases or whatever. So that's kind of really driving home the point of how the model makes its predictions. And lastly, this is the AUC ROC curves once again that I was going about. So again, remember, this is your true positive rate and this is your false positive rate. A true positive is that the model says that you have cancer and you actually do have cancer. So this was it was a correct case. False positive is the model says that I think this patient has cancer, but the patient did not have cancer, so the model was wrong. So the AUC, area under the curve, is that this is how well the model performed. And you look at the area under this curve, you look at all this area under this line, and you get a metric. So this metric will be somewhere between 0 and 1. So ideally, the way AUC ROCs work is that an AUC ROC of 0.7 to 0.8 is considered fair, it's all right. An AUC above 0.80 is considered pretty good, really good. And an AUC above 0.90 is considered excellent. It's an amazing model. So this model, let's say our machine learning model had a 0.76, AUC. That means that it's pretty decent. It calculates more true positives and false positives, but there's room for improvement. So that's an interpretation of this graph. Again, it's something that none of you have ever seen before. It's something that's brand new, and I don't expect anyone to know what it is. But this is something that we'll be covering shortly in the actual code. So that's just something important to know. So now I wanted to just get into the fundamentals of, what is machine learning and how does machine learning work? And I really want to, drive home the whole, you train, you test, you assess. So you look at these data that it's labeled and you say these patients have cancer and don't have cancer. You learn as a machine learning model, what is cancer? What kinds of patients have cancer? Generally, they're older, they smoke, yada, yada, yada. What kinds of patients don't have cancer? They're younger, they don't smoke. And you're able to make these kind of analyses. And then you test on new patients who you've never seen before. So you blind yourself from seeing what the results are, and you make these predictions on what do I think the actual answer is. And then you check the back of the book and you check the actual answer and compare it against what your prediction was to see what your accuracy is and generate these AUC ROC curves. All these curves are is basically showing how good are you at identifying actual cases of cancer. So now I want to get into the fundamentals of how machine learning works. So I'm just teaching you all this very, very conceptually. So this might not be very accurate, but this is very, very conceptual and very, very, helpful for understanding how AI and machine learning works. So when people say that I built a machine learning model, what they mean is that they just built an equation. So going all the way back to, middle school, primary school, whatever, whenever we learned algebra, think about this equation, y equals mx plus b, y equals 2x plus 1. So let's say x represents apples and y represents money. If I sell 1 apple, I make $3. If I sell 10 apples, I make $21, right? I'm putting in inputs into this x. I'm putting in inputs into this variable. And then I get an ultimate output for a prediction. In this case, this is a very simple prediction model. If I was saying, how many apples do I have and how much money do I have? Another thing in a clinical application, and again, this isn't true, I'm just saying this conceptually, is with age and number of cancer cells. So this isn't medically accurate, but it's very important for you all to understand how this works conceptually. So let's say that this variable represented your age, and this variable, the y output variable, represented how many cancer cells you have. So let's say if I was 10 years old, then I have 21 cancer cells. If I was 100 years old, I'd put in 100 here and I have 201 cancer cells. So that's my kind of model for predicting how many cancer cells you have. Now, in reality, machine learning models are far more complex. So they actually look a little bit more like this, where every letter you see here is a new variable, and the y output variable is a probability between 0 and 1. So what goes into every single variable you see here is dependent on what our data frames look like. So maybe the first data frame is sex, which is your gender, right? Male or female, 0 or 1. So then you put that into here. So maybe you have 32 times 1, or something like that. And then maybe you have like your height. So then you have, height as the next variable. So you have 386 times whatever height you have. And then you keep on doing this and you have all these multiplications and additions. And ultimately, you'll get a score like 0.9. So let's say we're talking about who has cancer and who doesn't have cancer. So machine learning models are very number-based. So that's why we convert everything from letters like text to numbers. So if you'll see here for sex, which is gender, male or female, instead of saying, male or female, we have to say 1 or 0. Because to a machine learning model, what is 32 times male, right? That doesn't make sense. So we have to say 32 times 1, which is male, or times 0, which is female, or something like that, to go and generate a type of model. And the ultimate probability, let's say we're saying, do you have cancer or not? 0 would be you don't have cancer. 1 would be you do have cancer. So then if the model outputs a score like 0.01, then you know that, okay, that's pretty close to 0. So that means this patient probably does not have cancer. Let's say the model gives you a score of 0.95. That means that, oh, that's pretty close to 1. So that means this patient does have cancer. And that's how the model generates these risk scores. It's not important to understand the math. I'm just telling you conceptually, the model will make this kind of big multivariable equation. And that's kind of how machine learning works. And it's all based on these data frames. So this data frame over here is actually the data frame that we ourselves will be using. So this is the data frame we'll be using for post-surgical cancer patients to see who lives or who dies. So these are tons of variables. So you have your sex, which is your male or female. Were you an inpatient or outpatient? So how long did you spend in the hospital? Your age, how tall you were, your weight. This is alcohol. ETOH is alcohol. Did you drink alcohol or not? Were you an alcoholic? Do you have trouble breathing? Do you have a history of COPD, which is a respiratory illness? Do you have pneumonia? All these different kinds of factors. Did you smoke? How many packs of cigarettes did you smoke? So all these factors here are numbers, and all of these go into the different variables here for a machine learning model to make some kind of prediction. So this kind of really takes us back. And again, I'm going to be repeating this a lot. You might get annoyed, but trust me, it's very, very important. So a machine learning model is going to train on the data. So I'm going to give it all this data, and I'm going to label and say, oh, this patient died. This patient didn't die. The machine learning model is going to study and say, well, okay, what kind of patients die and don't die? Maybe they smoke more cigarettes. Maybe they're older. Maybe they weigh more. Then it's going to test on a certain portion of the data. There's a certain portion of the data that we will know who lived, who died, and who lived. So the machine learning model will pretend to blind itself and say, okay, like I'm going to pretend I don't see the answer, and I'm going to guess based on what I've learned and trained on to say, I think this patient will die, this patient will live. And then at the end, it makes itself unblinded. It looks at the actual answer and says, okay, I was right for these 10 patients. I was wrong for this one patient. And it generates this accuracy score and an AUC ROC score. So this one more note that I want to make here, and this isn't important for our data because I've already pre-processed it. But there's one more step beyond all this with training, testing, and assessing called pre-processing. So pre-processing is basically making sure that the data you're passing in is clean and is something the model can go and work with. So this, in our analogy, if training and testing is like studying and taking an exam, pre-processing is ordering your notes and making sure that your notes are clean, your notes are legible, you can read your notes, it's in a language you understand, and then you can study on notes you understand. So basically, all pre-processing is that you want to get rid of any missing values. So medical data is not perfect. And that's something that I want everyone here to kind of learn more about. That there's going to be lots of patients who don't have data. So the doctor maybe messed up and forgot to log it. Maybe the patient just didn't have the data. So there's lots of blank values. So there's two things we can do. We can either drop or get rid of it. So we can say that if any patient doesn't have all their data, we just drop them, we get rid of them. So we omit them from the data frame, we remove them from the data, or we can impute them. Again, this isn't important to fully learn about, but I'm just introducing this concept to you so you can understand what it means. So imputing basically means that you put the average value of the entire column for a missing value. So I'm going to repeat this one more time. So let's say that I had a column for age, and all my patients were age 50, 50, 50, 50, 50, 50. And one patient, they had a missing age, and everyone else was 50, 50, 50, 50, 50. So even if this isn't 100% accurate, one thing we can do is that we can average up every other value in the column and put in the average value. So even if this patient's age is missing, I can average, if everyone else is 50, then I can take the average 50 and put it in for that missing patient's value. So I don't have to omit the patient from the data frame. So this is how imputing works. So I'm going to draw everyone's attention to this column over here, this second column. So NaN means a missing value, means no available number essentially. So this means that this patient doesn't have data here. So one thing we can do is we can remove this patient entirely, but then we have less data to work with. What we can do instead is average the remaining values in this column and put it in here. So just as an exercise, do this with me. Everyone else in the column, you have 5 plus 17 is 22. 22 plus 10 is 32. 32 plus 8 is 40. So then we had 40 over 1, 2, 3, 4 patients. So 40 divided by 4 is 10. So you would impute a 10 in this value right here. And that's exactly what we do after imputing. And same thing for all the other missing values. So again, that's really like, I'm just telling you that this process exists. The data we'll be working with is already pre-processed. So you do not have to worry about it. But so we'll have very clean data. There'll be no missing values. That's just something that I wanted to tell everyone about. And lastly, pre-processing means that turning everything into numbers. So this goes back to my original point of machine learning models are just equations. So what is 32 times yes? Or what is 94 times no? That doesn't make sense. That's why you want to replace any text variables like yes or no with a 1 or 0. So it's very easy to keep track of. And that's something like that's very, very simple for you to do. It's something that's simple for the model to take in. Because machine learning models can only understand numbers. So if you have something like male, female, you replace it with 0, 1. You have something like yes, no, you replace it with 1, 0. So you'll know what it means. And the machine learning model will also know what it means. And that will help it make better predictions. So like I said, our data is already pre-processed. So we can just go into the coding component now. Before I go into the coding component, I'm going to pause for just 10 seconds. Does anyone have any questions about anything I covered? So I covered a lot about what is machine learning, how does the model make predictions, how the equations work, how to kind of clean up your data. We covered a lot right now. So does anyone have any questions about any of this process? I'll pause for 10 seconds in case anyone has a question. Okay, great. Looks like no one has questions. You can feel free to ask them in the chat if you do, but I'm going to continue. So we're almost done here. So the workshop's actually taking a lot quicker than I anticipated, which is great. But now we're going to go over the coding and the basics of Python. So before we go into all of this detail, I want to make a note on complicated code. So I'm going to make an analogy with math. So let's say I have all these complicated equations that are differential equations and derivatives. So let's say you can understand the nuances of all these mathematical concepts. You can learn all this math and understand every single step, every single operation, and you can get to your end result, which is 0. And you can understand all of that with lots of detail. Or you can just think of it technically as 1 minus 1 equals 0. So you can go through all this complicated stuff and you get the end result, which is 0. Or you can think of it as something a lot simpler. You can think of it as 1 minus 1 and you get a very simple answer. Now, why am I talking about something as silly as math like this? This is a very important kind of concept I want to teach you all with code. Obviously, it's very important to learn the nuances and the specifics of how all this works. But in this workshop, I want to give you all a big picture understanding, conceptual understanding of what this means. So you don't have to understand every single nuance of all of this. Like instead of looking at all of this and seeing, oh my God, this is so much code, you can look at all of this and instead think of it as, okay, this is generally code that helps us see how the model performs by showing us a curve. So instead of having to understand all of this, you can just say, okay, this is code that shows me the AUC ROC curve. So you can kind of ignore how complex all this is and just say in your head, this is just code that shows me the AUC ROC curve. That's it, period. So that's kind of the note I wanted to make here. So there's a lot of instances when we're going over the code that it might not make a lot of sense to you because you don't have coding experience or you don't understand a lot about it. But in your head, just take it for granted what I'm telling you. And I have these notes in there just to tell you, like, this just generates our AUC ROC curve to show you how good the model is. So you can just read that and say, okay, this code is just generating this model. And then you can just look at the model and you don't have to worry about the code. So that's just kind of the trick that I'm trying to tell you all for now as you're starting out. Obviously, as you go later, it's really important to understand the specifics, but for now, you can just have a higher level understanding. So now I want to kind of talk a little bit more about this idea of data frames. So the data frames you can kind of save as variables in Python. So the same way that we can save, the idea of 2x plus 1, we can save this operation as y. So I can either say y, but that means 2x plus 1. So if I can go, instead of having to add 1 to 2x plus 1, I can say y plus 1. So anything I do to 2x plus 1, I can do to y. So the same way that I can treat, 2x plus 1 and save it as a variable, that's exactly what I do with data frames. So let's say I have this whole data frame over here. I can save it as a variable, and I can call this variable anything I want. So I can say df, that stands for data frame. So I can say df equals this data frame. And then if I want to go and do operations on this data, I don't have to go manually and do it to all of this data. I can just do it to df. So let's say I wanted to multiply all these data points by 2. I can just say df times 2. Let's say I want to go and look at the first couple data points or whatever. I can do that through df. And what's important to note is that you can call your data whatever you want. I'm just calling it df because that's the convention. You can call it data and say data equals this data frame. I can call it apple and say apple equals this data frame. I can call it Pikachu and say Pikachu equals this data frame. You can call it whatever name you want. And that's why computer science is kind of cool, because you get lots of flexibility with calling things different names and doing different things to different names. So the first operation I want to tell you all about, so it's in a package called pandas. It's really not important for you all to know the names and all that, but basically you can do different functions for what you call your data frame. So I did this kind of intentionally, but the function dot head and your 2 parentheses that shows you the first 5 rows of a data frame. So let's say I have data that has 1 million rows, right? Obviously, you don't want to see 1 million rows in front of you because that's a lot to analyze. So it's very common for machine learning people or just any kind of computer scientist to just say dot head and look at your data frame, and you just see the first 5 rows. And that's so much easier because now you have less data, it doesn't crowd up your screen, and you can kind of analyze generally, what does my data look like? So if you call your data frame df, you will say df dot head. But let's say you call instead of calling your data frame df, let's say you called it data, D-A-T-A. Then you'd say data dot head, and you'd see the first 5 rows. If I called it Pikachu, then I'd say Pikachu dot head. So it really depends what you call it, what name you assign your data frame. But either you'll call it data frame, df, data, whatever, dot head, that shows you the first 5 rows. So that's the first kind of command we'll be working with. The second kind of command we'll be working with is called df dot shape. So dot shape is very, very simple. If you say dot shape, then it outputs how many rows and how many columns you have. So the data we'll be working with, that I encourage you all to download, the JMA XREPU cancer death files. So that will output 5,000, 36. So the first number is your rows. The next number is your columns. So like I keep telling you with patient data frames, all the columns are patient attributes. So if you have 38 columns, that means you have 38 attributes of age, height, weight, do you smoke or not, what kind of diseases do you have? And if you have 5,000 rows, that means you have 5,000 patients you get to analyze with. So this data I kind of took and I anonymized from an existing data set. So the actual original data set had like 180,000 patients, but I generated synthetic data for you all to work with to avoid any privacy concerns for those patients. But working with 5,000 patients with 36 different column attributes. So that's what df.shape is. If I call my data frame data, it would be data.shape. If I call it mango, it would be mango.shape, just to give you the idea. So that really is the kind of fundamentals of what we'll be doing. And once we assign the data frame and we can kind of analyze and look at it, then we can build a model to train on all the data and study, well, who lives versus who dies. Let's look at the patients that live and die and look at correlations between them. We'll test it on another part of the data, and the model will then go and make predictions for a portion of the patients. Generally, it's about you train on 80% of the patients to learn correlations, and you test on 20% of the patients to see, was it right on who had cancer, was it wrong on who had cancer? And lastly, you'll assess and see, and look at the answers for the patients you tested on and see how many were you right from, and generate the accuracy and AUC ROC. So now what I want to do is, that's kind of it. So we're going to go now and jump into the code and kind of experiment with it. So I'm going to go and send the code, the link for the code in the chat. I sent it to you all as an email, but I'm putting it all in the Zoom chat right now. So please click on this in the Zoom chat, and this is what it will look like. So I'm going to open up a new incognito session to, or just a new session to show you. Actually, I don't have to do. I'll just do that here. So when you click on this link, I just sent it in the chat. When you click on this link, and please do that right now, you'll see this whole thing open up. So you all don't have permission to edit this directly because this is kind of my copy. So what you have to do is go to File and go to Save a Copy in Drive. So when you click on that, it will make a new copy for your Google account. So I'm going to give everyone about 15 seconds to go ahead and do that. So again, click on the link that I sent in the chat. It will send you to the Codelab page. And then you go to File and Save a Copy in Drive. So click and do that. So I'm going to give you all 15 seconds to do that. So go ahead and do that and type any questions in the chat. All right, great. Looks like everyone's getting it. So the next thing you have to do once you make a copy is that you have to load a file into Codelab. So here's one important thing about machine learning. Obviously, you'll be working with a data file. So it'll show you the image of this data frame. That's only because I loaded it on my end. So you actually don't have the data files on your end. So you have to load it into Codelab. So the way you do that is if you go to the left-hand side, if you go to the very left-hand side, you'll see something that says Files. Click on this Files option in the left-hand side. So if you click on that, this whole menu will appear. So I'm going to give everyone another, like 10 seconds to do this. So once you make a copy of the Codelab file, you'll be able to edit it. You'll be able to upload files. So then you click on in the left-hand side Files and just open up this kind of window tab here. So it will just say probably sample data. You won't have any file actually loaded in. So I'm going to give everyone 10 seconds to do that and click on Files. So once you go to the left-hand side and you click on Files, then you want to upload the file. So this is all steps I sent in the video, but I'm just walking through in case anyone hasn't done it before. So, and also so you have future reference for how to do it. So then you click on Upload to Session Storage. So after you go to Files, that's in the top left-hand side, Upload to Session Storage. Then this whole, like your computer screen will open up, and the file you just downloaded, JMA-X REPU Workshop Predict Cancer Death Cases. So you want to upload that file. You just click that, and you upload that file into here. And it will be loading here. And then once it finishes loading, you'll know that it's loaded into the data. So do that. So again, you click on Upload to Session Storage, and you'll upload the JMA-X REPU Workshop Predict Cancer Death file that I told you all to download from the email. So it should take less than 5 seconds for it to actually fully upload. But once it fully uploads, then you can just X out of here after it's done uploading. And then now we can all work with the code. So I'm going to give everyone another 5 seconds to go and make sure that you properly went to Files, Upload File, and you uploaded this JMA REPU file. So I'm just going to go and give you 10 seconds to do that. And while you do, I'll be kind of talking about the file. So this file is called a CSV file, a comma separated value file. That's not really important to understand what that means. It basically is just a file in a format that machine learning models can understand. These files are very common, and you can open them in Microsoft Excel. You can open them in Google Docs to look at what the data and what the file looks like. Yeah, someone asked me to repeat how it uploads. More than happy to do that. So you go on the left-hand side to Files. So on your Codelab notebook, you go to Files. So it's this tiny little folder over here that it looks like a folder. It says File. You click on that. Then when you click on Files, right under Files over here, you'll see 3 different options. You'll see an option to upload to session storage, and then 2 other options. The option you want to do is upload to session storage. It's the very first one under Files that says upload to session storage. So if you hover over it, it says upload to session storage. So you click on it then, and then a list of files will come up. So the file you want to click on is the file I told you all to download from the email, the JMA-X REPU Workshop. That's a file I sent in the email. So if you haven't downloaded it, all you do is you just go to the email I sent and you click on the download button, and it should automatically download into your computer. And then once you click on this, it just automatically uploads. And you know it's uploaded if it shows up over here. So Again, that's a CSV file. So this whole platform over here is called Google Colab. So you've all heard of Google Drive, Google Docs. So Google Colab is Google Docs, but for code. So you can run the code and you can actually run it on Google's processing power, just the way Google Docs kind of runs. So you don't have to use your computer's processing power. So it's very, very nice and easy to use. So every kind of box or chunk you see here is called a cell. So these are cells of code that you want to run. So if you hover over a cell of code, then you see this little button over here that says run cell. And it looks like this, like a little play button like you see on YouTube. So if you click this button, then it runs the cell. So if you click this button over here, it runs the cell, it'll be running, and then you see this little check mark box after it's finished running to let you know it ran. So the first step here is whenever you code, you have to import packages. So like I was telling you, like the df.head, df.shape kind of commands, these are preloaded packages. They're preloaded coding functions that are a little more complex, but they're really important for you to have to work with. So these are like pandas, which helps you look at the head of the file and read in the file. There's a lot of other kinds of files here called scikit-learn, sklearn, that is important for machine learning models for loading in different kinds of machine learning models. So you don't really have to understand what any of these packages are or do. You can just click run and it loads all these packages into your session. So that's all you have to do. You click the little button here, it loads, and then within 1 second, it finishes loading with a checkbox. Next, what we do is you want to read in the file. So this is already written for you. So the way you read in the file is that you can call the file anything, and you say the file's name is, this is the exact name of the file. So you don't want to change this. You want to leave this exactly as is, because that is the name of the file that we all loaded in right here. So you load in this file and you do these commands. So what these mean essentially is that I assign the name df to what this actual file is. So remember, this file is a data frame. So I can assign it any name I want. I can assign it the name data. I can assign it df. I can assign it mango, peach, Pikachu, Pokemon, whatever. It can be whatever I want. I'm going to call it df because that's conventional. Everyone calls data frames df, and it's very quick and easy to work with. And here's the commands I was telling you all about. So df.shape will tell us the shape of the data frame. The shape of the data frame lets us know that there's 5,000 patients and there's 36 features for the patients. There's 36 kind of medical features for all these patients. df.head lets us see the first 5 rows. So here are the first 5 patients, and I can see all their kind of factors. I can see their age, their height, do they smoke, do they have a history of congestive heart failure, which is a heart disease kind of thing, did they have weight loss, did they bleed, did they have sepsis? And over here at the very end, you can actually see the ultimate end variable we're using, called dOpper2D. So this is if the patient died within 30 days of surgery. So as you can see, the first patient here is a 0. They didn't die. The next patient here, 1. They died within 30 days of their surgery. This patient didn't, this patient did, so on and so forth. So it's very interesting data to kind of work with. So you want to click this button here and run this cell. And this cell should run for you, and you should see this kind of data frame appear for you. So that means that you've loaded in the data and you've been able to look at some important attributes. So next step, and this is what I told you all about, pre-processing. This is ordering your notes. This is making sure that the data has no missing values. The data has all numerical values. So you can check here and see that the data has all numerical values. So even for dOpper2D, it doesn't say yes, it doesn't say no, yes, no, yes. It says 0, 1, 0, 1. So these are all numbers. Good, check, that works out. The next step is making sure that there's not a lot of blanks or missing values for these patients. So this is kind of, I wrote you this reference code, so you can just go ahead and run it. When you run this code, when you click on this little run button, then you'll see a list of all of these attributes. The first attribute, it's my mistake. It should have been dropped. It's an irrelevant kind of variable. It should have been dropped. But as you can see, everything everywhere else says 0. So this code, what it does essentially is that it checks what percent of every column is missing. So as you can see here, every single column has 0% values missing because I did the pre-processing for you. I dropped any missing values. I imputed any missing values. So these are all 0. So if you saw a value here that was like 90, that means 90% of the values there are missing. So you should probably get rid of that variable. So that's a little bit of judgment and something you learn as you do more machine learning. But generally, if you have more than 50% missing, you want to drop or impute the value. But here you have no values missing, everything is represented, which is great. All your variables are present. So then the next step here is assigning our outcome variable. So this is a really important step. And this is where you can go and use this file for future data frames and just change around the outcome variable. So the same way that I told you how equations work, y is your outcome, x is your input. So you can say y equals 2x plus 1. Likewise, here by assigning a y variable, you say what is the outcome variable? What is your model predicting? So that's the most like, I'll say important part of machine learning, of like knowing what are you predicting? What is your outcome variable? So in this case, I told you all the outcome variable is d oper 2d. Remember all the way back from the beginning of this workshop, I said d oper 2d is does the patient die within 30 days or not? So we're just assigning this as a y variable. And this code essentially, if you even read it here, it says y value counts. Essentially, it shows you out of your output variable, what is the percentage composition of your output variable? So d oper 2d, your patient either died or they didn't die. And it shows you in your data frame, what percent of patients did not die, what percent of patients did die. So as we discussed, everything instead of yes and no is 1 and 0. So 0 is no, 1 is yes. So if it's a 0, it means the patient did not die. If it's a 1, it means the patient did die. So this percentage shows you that 62% of patients did not die within 30 days. Around 37.4% of patients did die within 30 days. This is important so you can look at the composition of this variable and see what the breakdown is. So if the variable was 99% of patients didn't die and only 1% of patients did die, that's not a good outcome variable because it's so imbalanced. Ideally, you want 50-50 because that's the most even distribution, but real data is messy. And you might get data with like 10% yes, did die, and 90% didn't die. But that's completely fine. That's something you kind of have to develop some intuition to work with. So that, sometimes, you might get different results for your data frame depending on what kind of data frame you have, but you want to click run there, and then it runs for what the data looks like. So I guess in this case, it's like, a different data frame. So this is what the full data looks like of, I guess 70% was didn't die and 28% did die. Around the same roughly. So one important thing here is that the output variable here is something you could change. So if you want, I would recommend follow through d oper 2d, but if you're feeling adventurous, here are other output variables. So in this data frame, there is a variable that says return OR. This is if your patient returned to the operating room or not. So that means ultimately your model would predict if your patient is at risk of returning to the operating room because of some kind of complication. There's a bleed dis, which is disseminated bleeding. So it's like, did your patient have a bleeding complication? Did they have a hemorrhage complication where they bled a lot? Which is important for doctors to know because there's special medication you can give and special kind of therapy you can give to those patients. So for example, if I wanted return OR to be my variable, I can copy paste it into the Y variable over here, and I can rerun it. And then I could see, oh, return OR only has 4% of represented patients. You can still build a machine learning model on that. It just wouldn't be ideal. If I wanted to test it for bleed dis, which is disseminated bleeding, I can just replace this variable right here. Just delete that and say bleed dis and look at the composition there. Again, it looks like not too many people were bleeding and the majority of them were not bleeding. So it's not a great outcome variable to look at. So the ideal outcome variable here is d oper 2d. It's the variable that we want to work with. So if you run it, you should get some kind of result like this, where you see about 70% of patients did not die and 28% of patients did die. So that's kind of, loading in the data frame, looking at the output variable. Now we get to the exciting stuff. We train. So remember, training is when we as humans train, it's like we're studying, we're looking at correlations. Training is when our machine learning model looks at the data and sees who died, who didn't die, and tries to associate these correlations here. So the first cell here, go ahead and run it. So all that does is associate an X and Y variable. So the X variable is the entire data frame. And if you see df.drop, that means that you're getting rid of a variable. So the reason you're doing this is that you're getting rid of your output variable right here. Now you might be wondering, Why are we doing that? Well, think about this. If I didn't drop the outcome variable, it's like you're testing. It's like you're testing on data that you already understand. So it's like you're taking a test, but you have the answers right next to you. So for the X variable, you want all the data frame except for the outcome variable. For the Y variable, you want just the outcome variable, which is your D/D, did your patient die? So you can go ahead and run that code, and then it runs right through. And one note I want to make here is that you have test size. So like I was telling you all, out of your entire data frame, you want to train on 80% and test on 20%. That's pretty standard. You might see some people say 70%, 30%, whatever, it kind of varies, but generally that's a split off. So this test size means that I am training on 80% of the data and I'm testing on the last 20%. And when I test on the last 20%, it means that I blind myself to what the actual results are. I have the results for who dies or not, but the model makes predictions on who it thinks lives or dies, and then it compares it against the actual value, which is important. This, you can just run right through. It shows you, it generates an array of your testing. That's really like less important for you to know. And this is probably the most important part. So this, you can run right through. This is you establishing your machine learning model. So there's lots of machine learning models out there. The three main ones are logistic regression, random forest, and XGBoost, extreme gradient boosting. So what this machine learning model does conceptually, it's really not important for you to understand all the details of how it works, but conceptually, what it does is that it looks at every single feature and looks at, out of each feature, it has a yes and a no, or it has multiple numbers, and it looks at the most salient features, the most important features for death from a surgery, and then boosts those features, and then keeps on going down a kind of tree-like pattern to see what are the most important features. Maybe it's smoking, maybe it's age, maybe it's weight, maybe it's having a history of heart disease, and kind of amalgamates all of that for the most important features that cause you to die. So the XGBoost, extreme gradient boosting, is one of the most powerful machine learning models we have right now, and that's the one I use. So what this does over here in the code is that it says that the model you're using is XGB, extreme gradient boosting classifier. And then when you say model.fit on X train and Y train, all that does is that it takes this machine learning model and then fits it to our data. So remember what training means. Training means that you're analyzing the data and seeing, well, who lives, who dies, and you're understanding, you're learning, you're studying for the test. So when I'm fitting this model to it, it's like the model is studying for this test and studying the data and seeing who lives, who dies, and the model is given the answers here of who lives, who dies, and it's going and analyzing that and creating associations. So now that you run that, you should see the check mark here. So now we test. So now that we've trained, now that we have a model which has understood who lives, who dies, and it's looked at the answers, now it's time for a model to take a test, to go and see for the last 20% of patients, can our model go and predict who will live and who will die? So that's what you run this through. So you run this code here, and it's called, we called it a variable prediction probability. So the model goes and now predicts on the test set. So the model now looks at this test data and sees, can I predict who will live and who will die? So this is now the analogy of you taking a test. The model now took this test, as illustrated by this green checkbox, it all ran through. So the model took our test and says, for the last 20%, this is a model's predictions. So these are the risk scores. So remember I told you the model generates a risk score between 0 and 1. So 0 means that the patient did not die. The 1 would mean that the model thinks the patient will die. But in reality, the model generates numbers in between. So over here, for this patient, the model thinks that this patient has a 95% chance of dying. So that means the model will probably say that this patient dies. Over here, the model says that this patient has a 4% chance of dying. So that means that the model will probably classify them as no, did not die. So it generates all of these answers. So it's a model like just took the test. So now it's time to go and get an accuracy. This is us scoring the model. So if you run this through, then now you'll generate a model score. And as you'll see here, it should be something around 80-something%. So if you remember all the way back from this presentation, when I told you how good are doctors at predicting who lives or who dies, doctors are 20% accurate, around 20% accurate at predicting who lives versus who dies. So out of every 5 patients, if a doctor to say, I think this patient will live in 30 days, they're only right for 1 out of 5 patients. They're wrong for the rest 4 out of 5 patients. Our model is 83% accurate. This means that our model is 4 times more accurate than doctors, which means we just made a machine learning model that beats doctors. It's better, like fourfold better than predicting who will live versus who will die than doctors in the US, which is really, really solid. Obviously, 83% isn't like perfect, but it's really, really good in medical data. And now it's time for us to generate the ROC AUC curve. So this is kind of back to what I was telling you about. You can understand what all this kind of code does, but it's easier to look at this code and say, okay, it just generates our AUC ROC plot. Just take it for granted and run it. So, some of you might get different metrics here. So some of you might get 82% or 81%. That's just variances in how each model runs. So the model I developed is going to be a little more different from the model you developed, or the model that Brenda develops, or the model that another data scientist develops. So the model scores will be kind of similar. Maybe it's 81%, maybe it's 82%, maybe it's 83%, but that's what they look like. If you run the model multiple times, you might get the same result, you might get different results. It all kind of depends on what model you're fitting. So now it's time to go and generate the final metric here, our AUC ROC curve. So all our AUC ROC curve is doing at the higher level is seeing how good is our model at identifying true positives and identifying people who actually had cancer versus people who did not have cancer. So that's all this is doing. This is just fancy code to see, like, plotting this AUC ROC curve and doing it based on the test data. So if you run this data through, then you should get an AUC ROC plot that looks something like this. Maybe it's a little less, like 0.88, maybe it's a little more like 0.90, but this is generally what the AUC ROC looks like. So in general, I put this note for you. So a 0.5 AUC ROC is very bad. That would mean that it goes exactly like this in the middle, which means that the model has no ability to classify patients who died versus did not die. Because that means that if the line was in the middle, that means that you get as many true positives as false positives. So you're guessing at random. In general, if it's 0.6 to 0.7, that's like not that good. If it's 0.7 to 0.8, it's pretty fair. If it's 0.8 to 0.9, it's a very good AUC ROC. So it's good to get published. It's good to do other stuff with. And if you get above 0.9 AUC ROC, it's very excellent. So as you can see here, our model here is very, very good. So it's 0.89. It's like right there, around 0.9. So it's a pretty excellent AUC ROC. So our model is very good at classifying results. So some of you might, so someone says in the chat that they got an error. I can go and meet with you right after this. So a reason you might get an error is that you might have either you might have accidentally entered a number into any of this code, or you did not run everything before it. So just check that you actually ran everything before it. So if you're getting an error, then go all the way back to the top, of the data, and run, make sure to click on this run button and click on this play button for every single cell. So if you got an error, that means that you didn't click the run button for every single cell. So remember, you might see an image of the graph or whatever here initially, but that's just because that's the image from my notebook. So you have to rerun it to actually get the results on your end. So you have to remember to rerun and click this run button. But yeah, if you click this rerun button, then you'll get your AUC ROC curve, and it'll look, oh, I see, yeah. So you have to, if you try to generate the code multiple times, you'll get an error. So that's why you have to go to the top and then rerun all the code from the top. So yeah, so I got the same error as someone else there because you probably ran it multiple times. So the solution there is that you just run the file and make sure you click on the play buttons to run all the code everywhere else, and that generates your new model. But that's kind of the fundamentals of how this machine learning process works. And I'm just kind of going through it and trying to troubleshoot in case anyone's code threw an error. But does anyone else have any other questions? So as you go and run through all the code, then you should be able to get all your accuracy scores. And as you see, the accuracy score is a little bit different from 0.83 to 0.82, which is perfectly normal. And then you should be able to go and get your AUC ROC graph just like this. And as you can see, because I ran it multiple times, you get slightly different results. The last time was 0.89, this time it's 0.90, which is even excellent. But there's slight variations in how you develop the model, and that's just perfectly normal. So that's the fundamentals of machine learning, and it's a very, very important tool for you. And one thing I want to point out is that you can use this code for other data sets. So you only need to replace two things here if you want to use machine learning models for a new data set. So firstly, you would have to upload a new file that you want to work with. So let's say you want to work with another data set for predicting who dies for, I don't know, a different kind of operation, or predicting who has a bleeding complication in pregnancy. And you just replace the name with the name of the file, and you have to obviously upload the file over here, and you just replace the name. And the only other thing you have to replace is this y variable over here. So there's 3 places where we have d opportunity here, but obviously your new data frame will have a different kind of output variable. So maybe it's called death, or maybe it's called complication, or whatever. So you would just replace d opportunity with whatever the name of that variable is in these 3 locations, and you're good to go. Then you have your machine learning model. You can run all the code as the same, and you'll get an AUC ROC for that new data. And that's how machine learning model works. Someone asked a question, how can we know which variables have the stronger effect on prediction? That's a very, very, very good question. So that's code I haven't included here, but it's something called a model variable importance plot. So basically, there's other code you can run to see that for your model, what variables does it prioritize? So for this data, when we made it, the model prioritized stuff like smoking, stuff like age, stuff like prior history of cancer, and stuff like that. So there is actually a way to reverse engineer it and see what variables contribute the most. For the workshop, I want to keep it simple and I didn't include that. That definitely exists, and I might actually send that after this workshop as a follow-up. So I just want to leave with some concluding thoughts before we end this workshop. So we all today were able to develop machine learning models that were 4 times better than doctors at predicting who lives versus who dies. In the status quo, right now in the US alone, over 250,000 patients die from preventable medical mistakes. So this includes, the doctors messed up, the doctors gave the wrong treatment, the doctors, could have done a better job or better surgical job. This is a wonderful place for machine learning to be the future of medicine and be the future of healthcare in the next 50 years. So as time goes on, you will all be the future of our generation and will be the future of, the entire world and of science as a whole. And you can all lead the march to go and integrate AI, machine learning into healthcare to go and better patient outcomes. Really, it's beautiful because a lot of doctors don't have the training or background in machine learning to be able to go and implement it into their practice, which is where all of you can come in. I'm going to go and send some files to you all after this workshop, but I want to help you all get published. So one big thing is that you can all go and look at lots of publicly available data sets. You can go download the data, you can clean it up and pre-process it, and you can run these machine learning models just using and copy pasting the code that I sent you, and you can go get really good results. And based on those results, you can go and write them up and publish them to medical journals. You can publish them to CS journals, and you can get published in really high reputed journals. And that's really good for you because it'll help you get scholarships. It'll help you get more, better admissions for graduate school. And it can also help you get more exposure to the scientific community, and you'll learn more about how does machine learning work, what are nuances in what variables work and don't work, and what are good attributes to look after. So really, it's a really exciting space. And the last thing I want to leave you all off on is that you are all in a very uniquely situated position, that you're all, the vast majority of you are from Peru or South America, but you're all from all over the world. You're all in a unique position that most of you are college students or graduate students, and you're all experienced in science, and you all have an interest in science, and you all have a unique opportunity with REPU that you all have access to a mentorship network and lots of really helpful people to go and help you go and have an impact on the world. Now, because a lot of you are from places like Peru, there's lots of high school students there who don't have access to the same educational opportunities that you do with this workshop. A lot of high school students that can benefit from mentorship, from guidance in applying to college, in applying to scholarships to really go and heighten their education. Lots of high school students that you can teach about machine learning, teach about biology, teach about biotechnology. So in JMA, Junior Medical Academy, we're an international nonprofit, and we are blessed to be able to access students from over 30 countries. And what we really do, we really pride ourselves on, is our student teaching model. So essentially what we do is that we teach students just like you in places all over the world. And those students then go and open chapters in local high schools and teach students near them. And those students go and teach other students. And it's a kind of spillover model that helps access students all over the world. And this helps us access students in rural villages or kind of remote areas that don't have lots of Wi-Fi, don't have technology, and that are hard to reach for other kinds of educational initiatives. So you will all be the future of education here too. So a lot of you kind of indicated that you are interested in this JMA ambassadorship, that you were interested in going and teaching more students about science and technology. So what we do is that we will provide you with all the materials you need. We have an expansion folder, so we'll provide you with all the lessons, all the curriculum, all the PowerPoint slides. We'll provide you with even teacher guides. So we've made teacher guides painstakingly that teach you what to say on every single slide that we've ever created, what to draw, what analogies to make, what questions to ask, and they even have games you can play with the kids to really reinforce what they learn. And this is really exciting because so many students all over the world don't have the educational opportunity to go and learn more about biology. And maybe they're really interested. Maybe they're going to be the doctor of our future who saves thousands of patients. Maybe they can get scholarships to really good universities and learn more about science. But they just don't have that initial exposure to science to go and get interested in the field. And that's where you can all come in, where we will give you all the material, all the guidance, everything you need. So even if you don't know a lot about biology or biotechnology, we'll give you all the lessons, we'll give you all the guides that teach you how to teach. So they tell you what to say on every single slide, what to teach students, how to interact with them, what questions to ask them, what games to play, and we'll give you everything you need. And we'll even give you a detailed guide, a step-by-step guide as to how do you reach out to locations, how do you go and set up a chapter, how do you go and reach students, and we give you every single step of the way, we give you guidance there. So if any of you are interested, I'll send you a follow-up email on this, and you can all apply for JMA ambassadorship. As members of REPU, you all get priority as JMA ambassadors. So if you go to our JMA website at jma.education, and I'll send this to you all in an email so you don't have to worry about it, there's a tab on our website that talks about getting involved and that talks about ambassadorship. So if you click on ambassadorship for Junior Medical Academy, you'll see more details about this on how do you become an ambassador, how do you join any task forces you have. There's FAQs on is there an application, how different curriculums you can teach, and all you have to do is you click on become an ambassador and you fill out this really quick Google form. And the second you fill out this Google form, it's done, and we can give you fast track approval to becoming a JMA ambassador. And you'll become a JMA ambassador. We'll give you all the perks. You'll get international volunteer hours, and it's really good experience for when you apply to graduate school programs too and scholarships, because it shows that you had some kind of impact on your environment, some impact in your community. You were able to go and gain scientific knowledge and share it with other people and encourage other students to be interested in it and help other students get into college and get scholarships. It's a very, very kind of exciting, prestigious thing to do. So we'll send out an email if any of you are interested at all to sign up to be an ambassador, and we'll give you follow-up materials on guides and basically everything you need, and we'll help you all teach. So that's something that's interesting to you. Just keep an eye out for that. We will email you within the end of today, and we're really, really excited to go and see what comes out of that. So that's all we have for you today. Thank you so much for coming to our JMA and REPU machine learning workshop. And thank you so much to REPU for putting us in touch with all of you, both the online and offline crowds. Really, we're so excited to go and see where this impact goes. So that's all we have for you today. I will stay on in case anyone has any more questions, but if not, feel free to kind of leave.